exists for obvious reasons, right? Okay, so hopefully, and I also posted this, which the desalination team should take a look. There's something called American-made challenges sponsored by the DOE, Department of Energy. There's something, and this is the solar desalination prize. So the team who's looking at desalination should definitely take a look at them, looking at particularly the requirements. So it'll give you some ideas and solutions as well. Finally, I want to make sure everyone's okay with assignment 2. No questions? Okay. Yeah. Sure.
That is, how for solutions, are these a solution for the overall device itself, or more of a issue of outside factors?
Oh, it can be either. Yes. In fact, I prefer the latter to the former. But as engineers, we are kind of driven to the former. So either is fine. But if you can combine them, it would be even more impressive, right? But I'm completely open, yeah. And of course, if you have specific questions, you can just email me, Okay, and we can talk more at the end of the class if anyone asks more questions. So let's jump into today's lecture. So where are we in the schedule? So I want to make sure we're all on the same page. Today we're going to talk about statistical ray optics, which is a little bit of an abstract concept. So first of all, I need you to understand the concepts. I won't ask you to derive equations or really do a lot of algebra and things like that. That's what we have to do a little bit today. So just be aware of it, but I will try to emphasize the concepts. You need to have the conceptual understanding, okay? Thursday's assignment. Next week is fall break, as you guys know, so enjoy it. The week after that is the midterm. So on the 15th, I won't be here. I'll be in Boston. So that day we have a TA review, where what that means is that the TA will be here. You can come here with your questions if you have questions about how to answer the problems or whatever. Primarily just your time to study for the exam. Thursday, the exam's also here, so don't get confused. It's open book, and I'll post all the instructions, open internet, whatever, everything's open. You just can't talk to each other and communicate, text, whatever. That kind of stuff is not allowed, yes. You have plenty of practice problems there, and we will probably give you more practice problems. They're already there, okay? And will be during this time of the class. I should also make a preface, because I probably won't see you until the exam, is don't stress out too much about it. I would say in the 5 or 6 years I've taught this class, no one's ever finished the exam. So it's okay if you don't finish it. Okay, so don't stress out too much about it, I would say. I want you to understand the concepts and try to address it as best as you can. Okay? If you finish it, it's okay, that's great, okay? But just be aware of that. And it's only a fraction of the grade, right? There's a reason for that. Everything that was covered until the midterm review will be in the exam. Okay, so today's lecture, you need to understand the concepts, but it won't be like, I won't dive deep into this. Okay, I think that's about it. Bring your own paper. And we'll have a stapler, so you can staple them. Write your UID on each page if you don't mind, because sometimes we have problems that get lost. I can't think of anything else, but yeah. Again, don't stress out too much about it. The most important thing is understand the concepts, okay? We will give you points for, okay, I should also clarify, we'll give you points for steps. So I don't really particularly care that you got the final answer, the correct, exact answer. But if you show your thinking, how you're getting there, that's fine. You'll get most of the points. Okay. As you can think from my class, this is not a class where, it's not a mathematics heavy class, let's say. Right? It's conceptual. This is the most important thing. Okay. Of course, if you have any questions, we can email me. I'm pretty good about responding quickly, okay? All right, so today we're going to talk about statistical ray optics. So this is a, like I said, an abstract concept, but we are going to rely on this paper. Okay, so I should say a few things about this. So this paper is on the link on the website, so you can download it, read it. It's very, very interesting. This guy, Eli Blanovic, is a very famous guy. He's been nominated for the Nobel Prize several times. At that time, he was working at, I guess, Exxon Research. Then he was at another company, I think Lucent or something. Then he was at UCLA, and currently he's at Berkeley. Very, very, very smart guy. But the paper is written, I would say, in a language that you should be able to follow most of it. So I encourage you guys to read it. We're going to follow this to some extent to understand two concepts. One is how, when light gets into a solar cell, can we do something to the solar cell to increase the performance of the solar cell? And the answer is yes. We are going to talk about two specific concepts to do that in this class. Today we'll focus on one of those, referred to as light trapping. There's another lecture in the next, I think in November, that will talk in a bit more detail about this, okay? So the idea is not hard to understand. It has to, so far we have talked about geometrical optics, but primarily we talked about geometrical optics of regular things, spheres, circles, straight lines, whatever. What happens when they become very complex, and particularly when they become random, okay? So the idea is quite simple to conceptually think about. So imagine you have some medium, okay, where this surface is completely random, okay, and your light's coming in. What happens in here? And can we do some engineering of this randomness to improve the performance of this if it was a solar cell? Okay, and I'll give you the newspaper headline. The two concepts are the following. One, we can engineer the structure to increase the bounces of light inside this material qualitatively. So you can imagine light enters here, and then it'll bounce around. Okay, qualitatively, very, very hand wavy. Okay, right? It'll bounce because why? Because if this is air, it'll reflect a little bit. Some of it might escape. Some of it will get reflected back, reflect, and so on. Right? You want to increase the number of bounces because you can increase the probability that the light will be absorbed by the solar cell. Okay, common sense. So that's one. This is referred to as light trapping. You try to trap the light. Okay, that's first concept. The second concept we won't talk about too much today's lecture is the idea. We know that when light goes, we know, if you recall, if light goes from air to glass, a portion of the light will get reflected, right? A portion of it will get refracted. Portion that gets reflected will not enter the glass, right? And this reflection is what's called the Fresnel reflection. And you can see that, for instance, if you look at the window at a steep angle, you will see the other side. It'll act like a mirror. You won't see through it so well, right? That's a loss of light. But that's no good if this was a solar cell, because that means it's lost to the solar cell. It did not enter the solar cell. So you want to minimize this, right? And this concept is something called anti-reflection. So you're trying to reduce the reflection. So two concepts, that's it. We're going to focus on this today. Okay? And this is geometrical optics, so nothing brand new. So let's think about the basics. So I need to somehow, what do I do? It was a way to, sorry. Do that? No? Sorry, let me see if there's a way. Nope. Okay. Sorry, I don't know how to deal with that, but go back. We'll move this around as we need. Okay, so first of all, let's think about this material here. Okay, so we have some material. Think about like a solar cell, which has some refractive index n, but the refractive index changes with position x. Okay, and light's coming in from everywhere. So you think about this as a textured optical sheet bathed in black body radiation. Okay, so under equilibrium, we know that the temperature of this must equal the temperature of the surroundings. And then this is called thermal equilibrium. We can write down what's called an electromagnetic energy density. All it means is that how much energy is inside this material, okay, for a given temperature, a given wavelength, and so on. That's determined by this complicated looking equation, comes from Planck's radiation law. Not super important for us, except for one point that I'll point out. Actually, where's my, sorry, let me grab my laser pointer, because I can't reach up there. Guess I forgot. Okay, I'll point here. So this equation determines the energy density of electromagnetic field. So how much energy in light is within that material, okay? So this K here is the important point that we want to look at. Of course, this is a function of frequency omega, K, which is n omega over C, okay? And a bunch of other things, not so important for us. Now, this n is the critical factor here. So if I try to compute the intensity of light within this material, it can be written as the density of electromagnetic energy density multiplied by something called the group velocity, okay, Vg. So you can see that. If I multiply it out, you get an expression which looks like here. Now, the only thing I want you to see is this thing right here. Okay, this n squared. So you can see that the intensity of light is proportional to the square of the refractive index of the material. This comes from quantum theory, Planck's law. But from our point of view, this is relevant to the previous lecture where we talked about concentrating the light beyond to an intensity beyond that of the surface of the sun. If you remember, we talked about this. And the way you did that was by using this n squared. You're concentrating into some solid material, which has n greater than 1. Okay, so the first concept is that simply by having a material whose refractive index is greater than 1, we can expect the intensity inside the material under equilibrium conditions to be n squared times the intensity outside the material, which by itself is an interesting concept. So that just comes from quantum theory. And we don't have to make any assumptions here. Oops. This thing. Leave it there. Now, we're going to make one more assumption. The behavior of light rays is ergodic. Now, what ergodic simply refers to the fact that light becomes random. So once light enters this medium, let's imagine that light entered with straight lines, okay, direct sunlight from the sun, let's say. Once it enters this medium, it forgot in which direction it came from. Its angle became completely randomized inside this medium. This is what ergodic means. The light ray forgot the direction in which it came from. It lost its memory. It's a kind of an important assumption, a little bit abstract, but we'll try to make the point that this is actually a good assumption shortly. So just to understand it, ergodic assumption means that once the light the ray enters the medium, it forgets where and which direction it came from. Essentially refers to statistical randomness. So this ray of light came in. It can give rise to lots and lots of rays inside in all kinds of angles and all kinds of directions. All kinds of directions and all kinds of intensities. So there's two assumptions there. One is thermal equilibrium. So it gives you that n squared factor. And two is the statistical randomness. Now we can actually take the previous two assumptions and write a very simple expression. Okay. Well, just read it. The intensity within the medium in thermal equilibrium with a black body radiation is n squared times higher than its environment. So the intensity inside the medium, this refers to internal, some function of frequency and space, is n squared times the intensity outside the medium. Ext is external. Now, n, of course, is a function of frequency. We should be aware of it. Remember, it changes with spectrum and position. This is not so important for us. And this simply refers to the black body. Okay, so far, should be pretty straightforward. Okay, now, this is the idea of the ergodic behavior again. So let's imagine collimated light coming in from the top. Collimated means one direction. Okay. Once it enters this medium, now you can see it's a little bit random on the top and bottom. It gets randomized. So it refracts in from the first interface here. Then it reflects here, following the local tangent of the surface, right? Based on this tangent, it will reflect. So if this tangent is random, of course, the angle is random. Then it reflects again, or it can escape the system if it's within the escape cone. We'll talk about that also. So we can show that if you send in highly directional light into such a material, it can very quickly get randomized. We can show that this is true as long as the rays are ergodic, that is, they forget the initial direction after one or two reflections. And when we talk about rays, we always talk about some statistical averaging in area, meaning we don't talk about a single ray. It's usually some region. So a solar cell has some size, right? So over that entire size, you average of all the rays. Okay. Just details, not terribly important, I would say, but you should appreciate it. I can do one more thing here, which is useful. Move that up. You can put a reflective surface in the back, which allows the light to get one more pass through the material. So the light bounces around here. Okay. And if you put a mirror down here, whatever light came out will get a chance to pass through it one more time. So probabilistically, you can get 2 times the pass. Okay, so in a lot of solar cells, you'll see the back side is, if you look from the top, ideally it should look black, right? It should be a black hole, all the light should go in, but that's never the case. But they try to put some reflective surface on the back side of the solar cell, which is behind the silicon. So you can't really see it. The silicon is opaque. Okay, so then you get this extra factor of 2. Same as before, but just added 2. So, okay, so now we have the basic ideas. So we have, we talked about the assumptions. One was the 2 assumptions so far, thermal equilibrium. Number 2 was this random behavior. We're going to make another point here. We're going to ignore absorption. We'll add absorption later on. Now, of course, if you ignore absorption, it's useless, right? Because the solar cell, you want to absorb the light. So just be aware of it. We will bring the absorption back shortly. Okay. Whatever we have talked about so far is only true for thin films, optically thin films. And this is a detail, but it's an important detail. We won't prove why this is the case. But the point is that the solar cell has to be, sorry, optically thick films, not thin films, the other way around. So it cannot be too thin, let's say. So the thickness of the films has to be larger than lambda over 2n. Okay, and we will ignore absorption for the time being. So let's try to understand what that means. So let's do a quick example here, very simple. Do it in your head on a piece of paper. So imagine we have wavelength of 1 micron, infrared. Refractive index is 3.5 in silicon. What is the smallest thickness this theory is valid? You can, so 1 micron divided by 2 times 3.5, right? So 1/7 microns, which is, it's about 1,000 by 7 nanometers. So what is that? 4, yeah, something like 141 nanometers. It's pretty thin. Okay, so it's almost a tenth of a micron, really, really thin. So the thickness doesn't have. So the point I want to appreciate, it doesn't need to be super thick. Even for very thin films, this idea is valid, which is important because a lot of times for the reason people try to do light trapping is because they want to make solar cells that are very, very thin, like inflexible or transparent or something like that. Okay, but it's not the only situation. Anything thicker will also work, but I'm saying it's also applicable for thin materials. And there are some advantages for thin solar cells. The second question, how much enhancement intensity is possible? We talked about it twice today, so. How much will the intensity be enhanced inside the silicon? Yeah, 2n squared, right? 2 because we had a mirror. If you can also say n squared and say there's no mirror, but let's imagine there's a mirror, right? Remember we talked about it twice. So 2 times 3.5 times 3.5. So what is this? 7 times 3.5, approximately what, 22 or so, something like that. Yeah. That's a pretty big number, right? So you're increasing the intensity by almost 20x. That's a huge number if you think about it. So it can be a huge effect. So I want you to get a sense of the scale of it. So it's worth understanding, worth doing this engineering. So it's not like a few percent or something, it's 200%, right? Or 2000%, right? Now, we should also understand what this whole ergodic behavior means. It has to do with the symmetry of how the light is bouncing around. I told you if that surface is random, that the light reflects off the surface. If that tangent is random, it gives a random angle. Now, what if you have a very regular structure like a billiard table? This cannot be ergodic because you can send a ball in any ray you want, but you'll only access 2 angles at most. And you can do this, it's pretty easy. I draw a line. You get 1 angle, and the next angle will have to be 90 degrees minus the other angle, right? Or something like that. I forget the exact number, but you can work it out. So you can only access a few number of angles. That means you cannot get an ergodic behavior here, okay? So yeah, so the number of angles accessible in a very high symmetry situation like this is only 2. You can think about a circle, right? And if you send the light through the center, well, it'll always be through, assuming it's normal to the surface. How many angles can you access? Well, what happens actually? It's a good question. It's a good exam question. Right? If I had a sphere of glass sitting in air, I send in a beam of light, what will happen to it? Well, let's see what happens here at this interface. Yes, you said something which is correct. Well, it is glass, right? Transparent, so something must go through, right? But some of it, you're right, will come straight back because of the Fresnel reflections we talked about, right? Everything will reflect, and that is only because of the fact that the refractive index of air is 1 and glass is 1.5. There's a difference, so you get some light back. That's a small fraction, typically like 4% or so. What happens to the remaining part? Correct. It will obey the Snell's law of refraction. What's it? Yeah, okay. But So what is the Snell's law? Sine theta I is equal to n times sine theta r. What is theta I? Yeah, what is the value in this situation? Anyone? Okay, let's draw it. Well, first of all, let's try to understand very quickly. This is the theta I, right? If this is the surface, sorry, I should draw the solid. This is the normal, that's theta I, and this is theta r, right? Everyone's okay with that? So here, I'm coming in normal, right? This is normal to the tangent of the surface, so theta I is 0, right? So that's 0. So n times, what should theta r be? Also 0. So what happens to the refracted ray? Go straight through. Go straight through the center of the circle. Okay. And then what happens here? Yeah, most of it will go straight through. Some of it will get reflected as well. Right? Same kind of situation. Okay. Make sure you're able to follow this kind of analysis. Very simple here in this situation. Right? So of course, this is not relevant to what I'm talking about here, except the fact that this is a very symmetrical structure, and I've accessed only one angle, 0. I came in with 0, went out with 0. Nothing else can happen unless I come in off axis. Then I can get other angles, which is actually a good homework problem. I think maybe it's in one of the example problems. What happens if I come in? We don't have time to go through this. What happens in this case? Well, why don't you guys draw it later? We will revisit at the end of the class. But that's the example of a question I can ask in the exam, right? You should be able to follow this. Okay, let's keep going. But the billiard table is highly symmetric. If you can increase the number of sides, for instance, with polygons, make it more random, you will see very quickly the rays can get randomized inside. This is the point that Eli makes in the paper, is that the natural state of the probability that light ends up being random is much higher than the probability that light ends up being not random. Because there are few cases with high symmetry, like the circle, billiard, square, rectangle, and so on, where the randomness does not occur. In most of reality, light automatically becomes random. So ergodicity is a good approximation. That's the point he's trying to make. But there are other things we should be aware of. Of course, light is not like billiard balls. They have photons, but they don't have mass, for instance, right? And our systems are not closed. And light can escape if the angle is smaller than the critical angle, right? So we never talked about this, and we will. Is if I had light coming in, it bends. By the way, what happens here? Goes out. And most importantly, this and this will be parallel. Okay. Now, if this surface is this parallel to each other, this rays have to be parallel to each other, right? Okay. Now, of course, if this angle, actually, this is not a good example, so I'm going to make this random now. Okay, I want to increase this angle, so I'm going to make this random. Okay. Light comes in, and let's say I refracted a larger angle. So it's not drawn properly, but let's say, whoops. Okay, that's more correct. And now this is greater than the critical angle. Then it will reflect, total internal reflection, right? So this escaped, because I guess I should draw this with a different color. But this is trapped. So we need to consider, so this theta is less than theta. We need to consider this cone of angles here as a range of angles over which the light can escape such a system. Okay, and we will try to analyze it. Yeah. So if you remember, comes from Snell's law. By the way, you don't need to memorize any of this. You can look it up. In the exam, it's not closed book, but you can very easily derive it from here. Critical angle means if I make this to be 90 degrees, that's the largest it can go. Cannot go more than 90 degrees, right? If I come in, this at most can go this way. Cannot go more. I mean, this, right? Okay. Actually, it's the opposite, my mistake, because critical angle means it's going from here to here. Okay, it's going from high index to low index, let's say, right? So I want to make, in this case, this will become I, this becomes R. Okay, I want to make this to be 90 degrees. Sine of 90 degrees is 1. This is n times sine theta. This is critical angle. So sine of theta's critical angle is 1 over n. But of course, you don't need to derive any of it. You can look it up, right? But I want you to conceptually understand why that is, what it is. Oh, so theta I is equal to theta C. I just made that, this is incident angle, and this is critical angle. They're equal now. I'm just saying what is the condition when the incident angle equals the critical angle. So we can calculate what the critical angle is. Okay. And that's the situation shown here. Okay, so this is an interesting situation. It's actually a real situation. For instance, in an LED. An LED light is generated. It's the opposite of the solar cell, right? Light is created, it has to escape. So in that case, the light's created right in the center here, that little explosion. And rays are going everywhere. But the vast majority of the rays don't go anywhere. They're trapped inside. A small portion of the rays within this cone angle will escape into air. Okay, and that cone angle is defined by the theta C. So this is a bad thing for LEDs, right? Because you want to get as much of it out as possible. So we will talk about this in a future lecture. But for now, for us, we'll treat this as a loss. Now, we don't want it to escape. We want everything to be trapped, because now we're talking about the opposite. We're talking about solar cell. We want it to be trapped, right? So we'll think of this as a loss or an escape cone. So sine theta C is 1 over n. And approximately the solid angle subtended by that cone is 1 over 2n squared by 4 pi. Don't need to remember any of this, but roughly, conceptually, if you want to think about 4 pi is a full sphere, and 1 over 2n squared, well, the half is, so maybe I should draw what I'm talking about. So the full sphere is 4 pi, right? But light is only going in half of the sphere, right? One hemisphere, so it's only 2 pi. And then we have 1 over n squared. 1 over n is the sine, and roughly solid angle is almost always sine squared. Okay, I'm hand waving here. We can prove all this, but you can think about it conceptually. Solid angle is 2 dimensions of the regular angle. So you square it, okay, sine squared, so that's 1 over n squared. So this 1 over n squared times 2 pi, 4 over 2 is 2, so you get the 2 pi. Now, if you had a transparent solar cell or a bifacial solar cell, which means light can go in both directions, then this 2 goes away. Okay, those exist. You can buy them. Something called a bifacial solar cell. There's 2 faces. And it is used in a very, very interesting situation, which I should draw very briefly. It is used, for instance, imagine that is a solar cell. It is used where, of course, you want all the light, let's say sun's coming this way, all the light here to be collected. Any light which is coming outside, you can put a mirror here and have it reflect. as much as possible. Some of it will escape. So you can get both sides. So it's used in a configuration like this.
Is that much different from this percentage of useful concept?
Yes.
It's more compact.
I see what you mean. Sorry, I think yeah, it is basically the same. Yeah, but if you sandwich two solar cells together, yeah, it'll just get thicker and you get more leads and things like that. You deal with it. Yeah, well, he's talking about, we'll talk about multi-layer later on, but he's talking about simply saying, okay, let's say I have a solar cell here where it's, all the power electronics or reflective surfaces on this side, this is transparent, light comes in. Why not just put them back to back and make it bifacial? It is bifacial. So you can go in this way or that way. All I'm saying is that there are actual cells which are made this way, where light comes in both directions. It's a little bit off topic. So the only reason I mentioned is that this too goes away in that situation. So just be aware of that. So the probability that a light ray inside the medium will escape is pretty small. Why? Because let's imagine that is a solid angle of the cone. That's roughly the probability light will escape. N is a big number, remember, 3.5 or something, right? So if I square it, remember I got 22 or something like that. Wait, what's 3.5 squared? It's not 22. It should be 11 or something. You have it? 12. 12, yeah. So it's about 12, right? In silicon. Times 2 is 24. 4 pi is what? Roughly 12. So this is about 12 divided by 24. Yeah, it's about a half or so. That's actually not too small. But generally speaking, it can be small. So the point is that a small amount of randomness is required to create ergodic behavior. It's a more natural state of the light once it enters any medium. Because remember, no solar cell is perfectly smooth as well, right? It's not, even if you don't create the randomness, they will naturally exist just from the manufacturing process. Okay, so we're a little slow. Let's go through some analysis here on how to deal with these concepts that we've learned so far. So we have to define some geometry. So we have this material here. Air is on top, and the material of some refractive index is on the bottom. Light is coming in from the top left at some angle here, I incident, it's intensity. The angle is phi here relative to the normal. The light is refracted based on Snell's law into this intensity, which INT refers to internal, okay? INC refers to incident. And there we have the loss cone. First, we're going to assume that a fraction of the light, some T INC, will be transmitted. And that is the Fresnel reflections we talked about. A small fraction here, 4%, is reflected off, 96% went through. That T is at 96%. So we're just generalizing that. Okay, it'll be different for different materials. It's a very important concept. The transmitted light must be balanced by the light that escapes the system under thermal equilibrium. Otherwise, it'll get hot or cold. So under thermal equilibrium, that cannot get hot or cold. It has to be steady temperature, which means light coming in must equal the light going out. Very important idea that we'll keep using it. This is called a principle of detail balance. We'll see this when we talk about the physics of solar cells. It's a very, very important concept. Okay, but the way we apply it here is quite simple. First of all, we're going to assume that the intensity of light inside that material that we just talked about is isotropic, meaning it's equal in all directions. Okay, and we can compute it quite simply by this integral. So we're going to assume that is the internal intensity per solid angle. Not so important because we're going to say it's uniform. So we have to, if it's not uniform, you have to do this integral over all the solid angles. I won't go through it. But we can simplify that this is independent of the angle. So that's the integral is simply cos theta, sine theta, d theta. This d omega now refers to the small solid angle. Converting d omega to d theta is very simple. It's just sine theta, d theta. Comes from solid geometry. So we just review, but we don't need to go through it in any detail. This integral is very easy to solve. You did this in high school. So B goes out of the integral and do it, and you get a very simple expression. The factor 2 comes from the assumption that we have a reflective back surface. Okay, so we get that. The internal intensity is just 2 pi times the intensity per unit solid angle. The intensity of light that escapes is very similar expression, except that now we are going to do the integral over from 0 to critical angle, that cone. Okay, everything else is basically the same, cos theta, sin theta. This part looks a little different because instead of the B internal, we have T escape, which is the probability that the light escapes. So we didn't talk about this too much, but you can kind of see it here. I said that some of the light bounces back here. Not everything escaped. So to account for that difference, you have this factor. Okay, we will remove all this, so don't worry too much about it. Integral is also the exact same as before. You end up with a very similar expression. I escape is how much intensity of light that is escaped is the internal intensity divided by 2n squared. Okay, that you can remember that comes from the previous expression we talked about, 4 pi over 2n squared. The probability of the escape cone comes from that. The 4 pi disappeared because we did the integral. And T bar escape is just some probability, some number between 0 and 1. Okay, not important. It's simply the escape transmission probability averaged over all the angles. Okay, so you look in all angles, it's average, what's the probability that light will escape. Now you apply detail balance. So this is the important part. Light in equals light out. Light in is simply the probability of light coming in multiplied by the incident intensity. Going out is just whatever escape, we just talked about it. Intensity inside multiplied by the probability it escapes. Okay, 2n squared just because of the escape cone. Put it together, you get a very straightforward expression. Okay, this factor T incident divided by T escape is usually 1. We can ignore it because more or less the probability of light passing from here to here is approximately the same as probability of light passing from here to here. You can think about this from reciprocity. You just turn time back, it should behave exactly the same way. Okay. If it doesn't, it will violate the second law of thermodynamics. So this will disappear for most purposes. There are some specific situations. The reason we leave it is because there are some specific situations it does not disappear. One example is in the CPC case. In the CPC case, if you have very, very high concentration, you restrict the angles to a very small slice of angles of the sun, let's say. You can increase the concentration dramatically. And that comes about because of this difference, actually. You can show it comes about. Of course, we proved it in a different way in the previous lecture, but you can actually prove it's exactly the same. Okay, you don't just need to appreciate it, I guess. So this is one for black body radiation, so we'll ignore it. So internal intensity is 2n squared times the incident intensity. Exactly the same as what we started off with. We just proved it using fairly simple, something called detail balance. Light in equals light out, okay, which we said at the very beginning. Okay, ignore this last point for now. Okay, the last part of the lecture, let's talk about light trapping, which is this idea that we drew before. So there are 5 situations here. The first situation is a parallel slab. Light goes in, light goes out in the same angle, parallel rays. Right, we drew that. Now I'm just adding a mirror at the back of it. So this is the worst case scenario for a solar cell. If I make a solar cell which is perfectly smooth on both sides, I get one pass through. That's not so good, right? I want to have lots of passes through this material. I want the light to spend a lot of time inside this material so it can be absorbed. Okay, we'll talk about what that absorption means when we talk about the semiconductor physics of solar cells. For now, let's not worry about it. I can put a mirror in. It gives me 2 passes, right? That's better than nothing. I can also texturize the top surface, which gives me even more passes. And this was a very common practice in all commercial solar cells, even in vast majority of solar cells today. The reason being that this kind of pyramidal structure is very easy to make in silicon. You just stick a certain crystalline structure of silicon in a bath, in a chemical liquid. And very quickly you create the structure because certain crystalline directions are dissolved faster than other directions. So it creates the structure very easily. You can, of course, make it more random and higher spatial frequency, so smaller features. So it allows you to get more angles out, scatter light more. Okay. And of course, you can do it on both surfaces. Yeah. Yes. Yeah, let's talk about this. That's an important point. It's actually, so you raise an important point. It's not just the passes that are important. It is the optical path length that's important. Okay, we talked about optical path length before. So let's just think about this, our solar cell for a second. Light came in. No, let's say I texturized this. So some light went out and it bounced around. Or maybe I shouldn't draw it that side. Bounced around, let's say. Okay. And then it escaped, let's say. Now the optical path length here is L1 times N, L2 times N, L3 times N, L4 times N, L5 times N, L6 times N. I'm trying to maximize this optical path length. I can do it in two ways. I can make it bounce around, a million times, right? So I have lots of them. The other thing is what he's saying. I can make it go at a super, 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 super large angle, right? We can achieve the same thing. But of course, you see a big problem with that. I need to make my solar cell super big. And there are other issues we'll talk about later on. But they're equivalent optically if you ignore everything else. It's the path length that matters. Yeah?
What it loses the energy more time.
Very good. We'll talk about that. So this is a very good point. This bounce is not 100% efficient. We will lose some energy here. So you're absolutely correct. It depends on what is happening here. My assumption here is that this is all bulk silicon. Down here, typically what happens is that you have contacts, right? Metal contacts and things like that. So it's useless. That light is absorbed in a metal, just heating it up. So not converted to electricity, typically speaking. Doesn't have to be the case, but typically. I just want you to appreciate that point. But generally speaking, you want large angles and more bounces, right? This kind of, you can intuitively imagine that's what you want to do, yeah?
So can you give us an example of glass random circle? I mean, is that?
Yeah.
Can we think of a glass in a bathroom or the bathroom?
Yeah, ground glass.
Is that
yeah, ground glass. So the privacy glass and things like that is simply random. Scatters the light, right? Correct. And the reason, well, so we have to be careful on how we define opacity. Because if I put a power meter and measure how much power is coming through the piece of glass, and it's a perfect piece of glass with no absorption inside it, it should be the same as if it was a clear glass. So, but you can, in other words, and this is an important point also, so let me take a minute. If I have a clear piece of glass, the light simply goes through, right, like that, right? And I can see through the window and I can form images of whatever is outside. But if I have ground glass, which typically looks like that, this ray came in and it got randomized, right? It lost its information. So if I look through here, the light might be the same amount that comes out, but its spatial information is lost. It's actually not lost. It's a Yeah, anyway, I won't go into it. It's a very deep topic, actually. My lab works a lot on this. It's an information theory of optics. Could be the same, yes. Important point. But yeah, the ground glass you were talking about. But these are examples of solar cells. So if you take a solar cell, open it up, the glass, you may not see in all of them, but you put it under electron microscope, it'll look like this. Very rough. This is either the silicon layer or something called silicon nitride, which is used for passivation, which means it tries to make the crystal structure of silicon nice and clean. So even though this looks kind of messy, the atomic structure of silicon has to be nice and clean with no dangling bonds. Dangling bonds are very bad for charge carriers, which we'll talk about when we talk about solar cells. Okay, but that's kind of what it looks like. Oops. So there are a couple of reasons why we want to do light trapping. Of course, we want to absorb the light very well, but also it's nice to have thinner solar cells because they can be flexible. Also, you use less material, so they can be cheaper, lighter, and good stuff like that. And there is a physical reason why thinner solar cells are also better, because you can have higher quality of the semiconductor with fewer defects because you have a thin material, not a very thick material. So you can control it better. And fewer defects means that you get, less carrier recombination, which is a loss mechanism in solar cells. So you can reduce the loss and increase efficiency. So two important reasons why light trapping is critical. We'll talk more about it. So now let's introduce absorption into the previous equations we talked about and just do the analysis very quickly. What happens when there's absorption? So the terminology is same as before. The input light is incident light intensity times the probability that the light enters. Now we're going to multiply it by area, so you get power. Okay, this is watts per meter squared multiplied by area, get the power. T is simply a probability, so it's a number between 0 and 1. Let's say it's 90%, whatever. Light will escape at some rate. Same thing as we calculated before, we just multiplied by some area A, which is the area over which the light can escape, which is written as ESC, but we're going to make all the A's the same, so not so important. Same equation as before. Now the absorption happens. The light is absorbed at the interface during reflection, which is what you pointed out and you asked before. We can model it simply by this eta here. Just some probability that the light is absorbed. We are not talking about the physics of how it's absorbed. That can vary widely. We'll just mathematically say, oh, some eta. 5% of the light, 1% of the light's absorbed, whatever, right? And the rest of the stuff is exactly what we saw before, twice. The integral looks exactly the same, 0 to pi over 2, all the angles over the hemisphere. Yeah? You have a question? Eta? What is dependent on wavelength? This can be wavelength dependent, yes. Yeah, yeah. Here we are assuming, here wavelength doesn't, well, it can go in here. A, of course, is not wavelength dependent because this is geometry. Lambda can go in here and here, but we're just assuming that it's averaged out for the purpose of this analysis. In reality, of course, yes, it depends. Okay. Then the integral is exactly the same. You get the exact same expression as before, except that now it's eta over 2. And remember, that was not critical angles pi over 2, so you get that half term. But anyway, this is a simple integrals you can do. So it is a fractional absorption. Now, of course, there's light is also absorbed in the bulk, right? So inside this region, the silicon, there's also absorption because it's not like glass, right? Silicon is opaque, light doesn't pass through. So some absorption is happening here. So we have to account for that. We account for that by this expression here, which looks complicated, but it's a, let's see, what's the best way? So the way to think about it is this alpha, which is an absorption coefficient multiplied by the intensity, multiplied by some volume element, then the solid angle as well. You integrate over the volume and the solid angle, and you get the expression. So here, what we did was we said the intensity is uniform, so it comes out of the integral. The volume simply becomes L, which is the effective thickness multiplied by 1. We're looking at a unit area for now. or L times A, actually it's not unitary. L times A is the volume, okay, so that it came out of the integral. And the remaining integral is something we've seen before, okay? And you get that expression. So this is something you might have seen in chemistry, high school chemistry and so on. This is very similar to what's called Beer-Lambert law, where the absorption in some material is simply the thickness of the material multiplied by an absorption coefficient. Just these two things, alpha and L. Everything else is not so critical. So the thicker the material, the more light is absorbed. Common sense, right? I want to make my silicon cell as thick as possible, but of course, high quality silicon can be expensive, so you don't really want to do that too much, right? And there are other problems or defects and things like that. Now we're going to apply a detailed balance. Light in equals light out. So on the left-hand side, it's light in, very simple, right? Incident light, only one term. Right-hand side is light out. Three things are happening. Some light is escaping out of the solar cell into the air. Some light is absorbed at the interface. Some light is absorbed in the bulk. These three terms. So the physics system, I mean, the concepts are simple. So three terms on the right-hand side, and you can solve the equation. There is a typo in the paper, so if you read it, just keep an eye on that. Everything else is simplification. Then our goal is to increase the absorption in the solar cell. So we have to compute how much energy is absorbed, how much power is absorbed. So that's simply 2 alpha L A times I, which was in the previous slide, right? We computed. This is how much was absorbed in the bulk. This is the part that we are interested in. This is the part that gets converted into electricity. Okay, this is what's absorbed inside the bulk of the silicon. So that's here, and we get this expression. Okay, looks complicated, but we're going to simplify it soon in the next slide. So the fraction of the incoming light that's absorbed. So you can think about, okay, if I get 100% of light coming in, what percentage of the light's absorbed inside the silicon? What percentage of the light is utilized? That's simply this stuff divided by what came in. Okay, and then you get some expression. Now we're going to simplify this. So of course, let's talk very quickly about how to simplify it. Very simple. We'll make all the A's the same. So this cancels out, all this cancels out. And we're going to say alpha is small, absorption is small, which is kind of not a great assumption, but it's true in many cases. So we're going to ignore that. We're also going to say eta is small. In other words, our reflections we talked about is highly efficient. We're going to throw that out. And then we get a very simple expression. We are also going to say this and this are the same, so this will also cancel out. So we'll simply take this on top. Okay, we'll see in the next slide. So consider, so we'll end up with, actually I should go back here. So I forgot to type. So all of this is gone. This is gone. This and this goes away. So this 2n squared goes on the top. So you get 2n squared times 2 alpha L. So 2 alpha L is what you would expect to see if nothing, you do nothing. So my enhancement is this 2n squared, which is of course the same as what we have talked about the whole class. It's consistent. It's just that we analyze it in a very different way by applying detailed balance. By the way, the reason I walked you through this is because detailed balance is a very important concept we will apply again when we think about solar cells, the efficiency of solar cells. So I know this is not easy concept, but you should review it. You should at least read the paper and review it. Okay, so now let's throw in some numbers. Consider the case of weak absorption. Silicon is an indirect bandgap semiconductor, which many of you know who have taken the 3200 class, which basically means alpha is small typically. Unless you're close to the bandgap, then alpha can become large. So this assumption breaks down, but not so important for us. So alpha is small. We're going to assume eta is small, as I said before. This means that the fractional absorption due to imperfect reflections is small. So it's ideal case. Also, those T, the probability of escape and incident and all that are the same. Then you get the maximum enhancement. 2 times 2n squared or 4n squared. Now, that's a big number, by the way, right? Again, n squared is about 12. Remember, 3.5 squared times 4. That's 48, right? It's a huge number, yeah.
So how this changes if the bottom silicon material is not parallel with the top?
So here, we don't care And in fact, our assumption, that's where this 2 comes from, is that we assumed there was a perfect reflector. In our assumption, we assumed that this was just a perfect reflector. That's why that factor of 2 came in.
If it's angled,
If the, you mean if this is rough too?
no, this is angled with respect to the top surface.
What do you mean? Let me draw.
You have top surface, if you said it's random.
So let's say top surface is random. What should I,
Bottom surface is under angle.
like that? Yeah, you can calculate it. It'll be different. Yeah, I mean, this is the maximum. So you can actually show this is the best you can do. Well, here we assumed a situation which looks like this actually in reality. We put in a perfect reflector in the back of 2 surfaces which are textured. And this is actually the same as simply putting a perfect reflector here. That's what I was saying. And this is an ideal situation, of course. In reality, you don't get a 50x enhancement. That doesn't exist because of practical concerns.
So you mentioned that, so 48 was that.
That's like the theoretical.
Percentage-wise, 40%.
No, times. That's why it's crazy. It's a crazy number, right? If you think about it.
48 times.
It's 4n squared is the enhancement and absorption times. So you can get, that's it. So it's the potential is huge. Yeah. But there are caveats here in the sense that if you make the silicon too thick, this starts breaking down. So it's only valid for a small thickness, which means that you're starting from a small absorption originally as well. So there's some caveats here. But again, my goal here was just so you understand conceptually what detail balance means and this idea of enhancing the absorption by light trapping. So all solar panels today utilize this idea in more sophisticated ways than we talked about, but all of them do. So let's look at how in the paper he experimentally verified this. This was just theory. It's also interesting to understand how this was verified because it's a very simple experiment. Just take a silicon wafer. Oh, that's a typo. VF. Okay. Put a reflective mirror on the back. It's a white surface because the mirror is not perfectly reflective for all the wavelengths, especially in the infrared. The silicon, you also want infrared. So you use a white reflector in this case. Then you have something called an integrating sphere, which simply collects all the light in all the angles and gives you a number, a power. Okay, just integrates all the light. Light's coming in from this side. Okay. Yeah, we don't need to know exactly. I mean, I can talk about it later. But so this, if it's a perfectly flat surface, you would expect light to pass through parallel, right? And it'll just reflect straight back. So the experiment was done with first a perfectly polished silicon wafer, 2 sides polished, and another silicon wafer where one side was textured. And then you compare what is measured by the integrating sphere. Simple experiment. Okay. The polished side faces the light. In that case, the rear surface is either flat or textured. The reflected light is measured by the integrating sphere. And the results are useful to understand. So the plot here is wavelength. Okay. This is wavelength is decreasing here. Just be aware of that. So that's red. This is infrared. The band gap of silicon is about here somewhere. What that means is that below this, the photons get absorbed very easily. Above this, photons don't get absorbed so easily. There's a band gap of silicon. So the first plot on the top is the fully polished silicon. In fact, if you look at a polished silicon, it looks like a mirror. You can see your face. You look at it. So, which means that in the visible light, almost in this experiment, almost very low amount is back scattered or reflected back compared to the infrared. Now, when you texturize it, what you see is that more of the light is absorbed within the silicon. So this starts dropping. So whatever is reflected back. So remember what we're measuring is what passed through the silicon reflected back into So if I measure less reflected back, I've absorbed that in here. So by texturizing the silicon, absorb more, that curve drops. Okay, and you also get this red shift of the spectrum, which is actually quite useful, which means that you can collect more of the sunlight. You're increasing the, reducing the bandwidth. So instead of just here, I'm collecting more. This will become more obvious later on. Don't wait too much more. And the last point I want to make is a slightly different configuration, which is also quite important, is this idea, what if we had little particles of silicon, granules of silicon embedded inside a polymer, okay, like plexiglass. Plexiglass is polymethyl methacrylate or PMMA, so we refer to it as PMMA, but it's nothing other than plexiglass. So the silicon granules embedded inside plexiglass. Now, why would you want to do this? Any? It's a sheet, not a fiber. It's a cross section of a sheet. You would want to do this because it can be transparent. Think of a window of a building or whatever. I mean, that was the idea back in the 90s. Okay. But it's not a perfectly transparent because you want to absorb some light. Otherwise, it's just, just a window, right? So it would be a multifunctional window. So the silicon microspheres are embedded inside the PMMA, which is plexiglass. Light is trapped in the silicon due to the higher index, which enhances the absorption. And of course, you can have a white backing to do the second reflection through it again. The analysis is very similar. We can go through it quickly. So the detail balance is you want to do on the left-hand side, light going from air to the PMMA, plus light going from silicon to the PMMA should equal light going out of the PMMA. PMMA to the air plus PMMA to the silicon. Okay, so that's the principle of detail balance. And the expressions are exactly the same as before, except that now we have different indices. So 1 refers to air, 2 refers to silicon, 3 refers to PMMA. Everything else is exactly the same. Okay, of course, we have different terms, but everything else is the same as what we derived. You can also apply the detail balance in silicon, which is what we are interested in. Okay, light goes from air to silicon, PMMA to silicon. That's the incoming to silicon. What is leaving silicon is silicon to air, silicon to PMMA, plus absorption in silicon. And this is the part we're most interested in. And you can write out the expression. The part we're most interested in is the third term. So we'll look at that. Actually, before we do that, so here we're going to throw in some numbers to look at I2, which is the intensity inside silicon. So the 2 refers to silicon. Okay. So the refractive index of silicon is 3.53. N3 is PMMA. Plexiglass is 1.5, just like glass. T12 is just a probability, so say it's 1, doesn't matter. So you get that expression. Okay, I2 intensity inside the silicon is some expression which depends on the thickness times alpha times the incident intensity coming from outside, air. Okay. Now within the band gap of silicon, we can set alpha as 0. It's all very small. So this disappears and you get this expression. And that is simply 2n2 squared times I1. If you multiply it all out, you'll get the same thing. The intensity inside the silicon is enhanced by, as we saw, 2n2 squared. Using that idea. So with the granules, 2 things happen just so we can conceptualize it. Light comes in, of course, can be absorbed directly. Light comes in, it can get trapped inside this polymer and then go to silicon, right? Bounce around and go to silicon. Or it can just pass straight through, which is the part which we will see that's transparent. Or if you put a mirror back here, it'll just bounce back. So you can experiment, do the exact same experiment as before, and measure something like this. So again, the wavelength here, that's the how much light is reflected back. If you don't have any silicon, everything is reflected back 100%. No absorption or very little absorption. There's only tiny little bits of silicon. By just adding the silicon granules, everything's absorbed. Okay. And this is a very important result because you can see here, for instance, at this wavelength, 50% of the light's absorbed, but the area covered by silicon in this example is much less than 50%. It's like 20% or so. In other words, roughly 20% of the area is covered by the silicon, but you're absorbing more than twice that in terms of light. So if you were to build a window, by using a little bit of silicon, where you've saved cost, you're able to absorb some of this light and convert into electricity, but you can see some of it passing through the window as well. So it'll be like a tinted window. This is an example. Of course, and that's my last slide, so I'll stop here. But